everybody. Welcome to section 5.3. We're going to talk about trigonometric functions of any angle this time. Whereas in the last unit, section 5.2, we stuck with right triangles only, we now expand this notion of being able to find trigonometric functions of right triangles into any angle in the plane. And to start off with, right over here, I have a drawing, and you can see I have an angle that is illustrated as being in a plane but greater than 90 degrees. Now, we can't use a right triangle directly here because right triangles only contain angles that are less than 90 degrees. So what do? Well, the key here is to recognize that in fact we have something called a reference angle. We have an angle enclosed in our figure right here that is less than 90 degrees. And so in a sense, as long as we know what our x and y value is, as long as we have some idea of where this angle actually terminates, we can treat this as a right triangle in the plane with a x side, which is our adjacent, a y side, which is our opposite side, and of course a hypotenuse. Now the hypotenuse is always a positive value, and the reason for that is by our Pythagorean theorem, the square of the adjacent side plus the square of the opposite side is always equal to the square of that hypotenuse. And although x and y could potentially be negative values, h is always a positive value. Okay, so how do we define our trigonometric function? Well, essentially, if we know what's going on right here in this figure, we can basically express our sine, cosine, tangent, etc. of our angle theta in terms of these x, y, and h values. For example, if I'm interested in finding the sine of that angle theta in the drawing, it will be the same as taking the y value dividing by h, which is the hypotenuse in this drawing. And to take the cosine of the angle, I will be taking the value of x over h, which is the adjacent side of the hypotenuse, bearing in mind that x or y could be negative values. The tangent of the angle theta would be equivalent to saying y over x, right? And then, of course, we have our other trigonometric functions, our reciprocals of the sine, which is the cosecant of the angle theta, which we'll treat as hypotenuse over opposite, h over y. The secant of the angle theta, which we treat as h over x, right? That's our hypotenuse over our adjacent side. And then, of course, our cotangent of the angle theta, which is the x over y. That's adjacent over opposite. So let's go through an example, just illustrate how this goes. Let's say that we want to find the exact value of 6 trigonometric functions of an angle in standard position such that the terminal side contains the point -3, -1. What could that possibly mean? So on our graph, what we're going to do is we're going to actually find the point -3, -1. So let's put that in our plane over here. I'm just going to label my x and y axis. And we're going to do a little bit of trigonometry with the values that we get. And we want, okay, here's 2, here's 4, here's -2, here's -4, here's -2, here's -4 along our y-axis, 2 and 4 along our positive y-axis. So if we take the point -3, -1, our point -3, -1 is located here, -3, -1. These are our x and y values, so like in our drawing above, we can put a line through that point here from the origin over and treat this as a right triangle problem. And in this right triangle problem, what we actually have right here is a right triangle contained within this little area right here. And we can talk about the lengths of the sides of this right triangle as being on opposite side of -1 and adjacent side of -3. And for our hypotenuse, we need to use our Pythagorean theorem. So we would say, well, h squared is equal to negative 1 squared plus negative 3 squared. Don't forget that the negatives do get squared in this arrangement, so h squared is equal to 1 plus 9, which is to say equal to 10. Therefore, the hypotenuse is given as the positive square root of 10, which is not reducible. But if we're interested in finding the trigonometric functions of our angle theta in standard position angle theta is measured this way. And so our sine of the angle theta would be given as negative 1, the opposite side, divided by square root of 10, or written another way, negative square root of 10 over 10. This is how we're going to express this without a calculator. We don't need to actually find the angle theta. We're just interested in the ratio. The cosine of our angle theta will be the ratio of the adjacent side, which in this case is negative 3 to the square root of 10, or rationalizing the denominator, negative 3 times the square root of 10 divided by 10. Our tangent of the angle theta is our opposite over adjacent. Our opposite side is negative 1. Our adjacent side is negative 3. So negative 1 over negative 3, which reduces as 1/3. And that would be our tangent of the angle theta. Then we continue on. We could take our reciprocal functions. So, for example, the cosecant of our angle theta is going to be square root of 10 over negative 1. So it's negative square root of 10. Our secant of the angle theta is our reciprocal of cosine. So we would take square root of 10 over negative 3, or the negative square root of 10 over 3 as our ratio. And then finally the cotangent of our angle theta, which would be the reciprocal of our tangent, 3 over 1, which we would just express as 3. And so that's exactly what we're looking for right here. Being able to find the values of our trigonometric functions of any angle of the plane tells us that we can get positive and negative values just depending on where we're at. More to come.